Alright guys, this is the 9-3 solving quadratic equations video. Today we're going to learn how, what we've been doing with factoring, how that relates to the x-intercepts or roots of a parabola or quadratic function. So a couple definitions here, if you guys could write these down. The first one is a quadratic equation. What is a quadratic equation? A quadratic equation is one of the form y equals ax squared plus bx plus c. And what makes it quadratic is that it is of second degree here. You'll see there's a degree of 2 on the first x listed there. And as we saw when we were factoring, when we would take our two factors, they would serve as the dimensions of a quadrilateral, specifically a rectangle. So that's what the box was when we were factoring, is when you pulled out the greatest common factor of each row and each column, you were finding the dimensions of a quadrilateral or rectangle. A root or zero, here's another definition for you. When we were factoring, we were actually finding something related to what we call the x-intercepts of a graph, or the roots or zeros are all the same thing. It's the places where the graph crosses the x-axis. You'll see here the green arrows pointing at those red dots. So right here in this equation, we can see that the roots or zeros or x-intercepts, whatever you want to call them, are 2 and -2, because that is what would make this equation over here, the x squared minus 4, equal to 0. If you plug in 2 and square it and then subtract 4, you'll see that we get 4 minus 4, which is 0. And I do get the same thing if I plugged in -2 and squared it and subtracted 4. I would also get 4 minus 4, or 0. And so for that reason, we call -2 and 2 the zeros of this quadratic equation, or the roots of the parabola that you see graphed over there. Now if I want to, there's actually a method I can go about for solving quadratic equations, at least ones that do not have this middle term bx that you see up here. If you have a quadratic equation with just the x squared and just the number, which we call the constant, you can actually solve it fairly simply. Let me write it down over here. X squared minus 4 equals 0. We know that we can go ahead and add the 4 to each side, so I'll do that right now. I have x squared equals 4 because 0 plus 4 is 4. And then the opposite operation of squaring a number is to take its square root. So we have x equals the square root of 4. Now there's something I should add here. There are two numbers that when squared equal 4. One of them is +2, the other one is -2. And so what you'll see here is that I have x equals the plus or minus, is how we say that, plus or minus square root of 4. So x equals plus or minus 2. And you'll notice that those values, x equals 2 or x equals -2, are the roots, here's one, here's the other, of the parabola that you see graphed here. Alright, we're going to solve by graphing. So it says graph, then find roots. So this is going to build on what you were just working on, just graphing quadratics, graphing parabolas. We did that in 9.1. It says graph, then find the roots. Now I just showed you how to solve the equation, so you could also do that. But we're going to graph by just trying some values here. So I'll make an xy table. And on my xy table, I'm going to plug in my typical -2, -1, 0, 1, and 2. And I might need to plug in more values than that. What I'm looking for here is where the graph of this equation crosses through the x-axis. So if I plug in -2 here, -2 squared is 4. And just show that right here, -2 squared minus 1 is 4, minus 1, which is 3. So the first one here is 3. If I plug in -1, -1 squared would be +1. 1 minus 1 is 0. And then if I plugged into that same spot 0, 0 squared is 0. 0 minus 1 is negative 1. And then if I plug in 1 and square it, I get 1. 1 squared is 1. Minus 1 is 0. And then 2 squared minus 1 would be back up to 3. So just like I got up here with negative 2. That was a negative 2 comma 3 I have up there. So negative 2 comma 3. So if I graph this, I have a point at negative 2 comma 3. Another one at negative 1, 0. Another one at 0, negative 1. Another one at 1 comma 0. And another one at 2 comma 3 up here. So if I draw the graph of my parabola, it looks like that. And you can see that the roots are x equals negative 1 on the left side, or x equals 1 on the right side. So that's x squared minus 1 equals 0. This one we have x squared equals 0. That's just saying that x has to be 0, and therefore y would have to be 0. We have as a root just x equals 0. That's kind of a strange one, but that's all that is. It's just a single point at 0, 0 for that equation. You'll notice on the next equation we have x squared plus 1 equals 0. If I go to graph this, something interesting is going to happen. I have an x and a y. I'm going to plug in negative 2, negative 1, 0, 1, and 2. And as I plug those in, negative 2 squared is 4. 4 plus 1 is 5. My board's a little off. I apologize here. Negative 1 squared is 1. 1 plus 1 is 2. 0 squared is 0. 0 plus 1 is 1. 1 squared plus 1 will give me back up to 2. And then 2 squared is 4. Plus 1 is back up to 5. So when I graph this one, you'll notice that I have the values 5, 2, 1, 2, and 5. So if I plot these points, I have negative 2, 5. I've got negative 1, 2. I've got 0, 1. I've got 1, 2. And then I've got 2, 5 up here. Notice that the parabola does not ever cross the x-axis right here. Here's the x-axis right down here. And it does not ever cross it. So therefore, we say this has no real roots, because the parabola does not cross through the x-axis like it did on the first example. All right, I'm going to show you one more thing here. Besides graphing, move this up a little bit. But besides graphing, we have another choice, and I demonstrated this on the first page. We can find solutions by simply solving the equation, not graphing it. We wouldn't want to graph this one here, the 3x squared minus 75. Really don't want to bother with graphing that, but if I take and add 75 to each side, let's try that again here. So add 75, it looks like the board is back to working again here. So we've got 3x squared equals 75, that's the first step. Go ahead and move this down now. Next step would be to divide each side by 3. So I have x squared equals 25. And because 25 is a perfect square, I can take x equals plus or minus 25, square root of 25, which gives me x equals plus or minus 5. And so I can circle that. That represents both of my roots. I have one root at x equals 5, one root at x equals negative 5. To demonstrate this, if I plugged in, let's plug in negative 5, for example, for x. I would square negative 5 and then subtract 75. Actually, I'm going to square negative 5, which is positive 25. Then I'm going to multiply it by 3. And you'll see that I get 0 on the left and 0 on the right. So that's my check. It shows that plus or minus 5 are in fact zeros of this original equation. If I plug in negative 5 or positive 5 for x squared, I will get 3 times 25 here. So right here I'm going to get 25 no matter whether I plug in negative 5 or positive 5. 3 times 25 is 75. 75 minus 0 is 0, so that is a 0 or root of that equation. Now, this next one is kind of like the one we see up above here, the one with no real roots. You'll see it's of the same form. I have x squared plus 1 equals 0. Here I have x squared plus 49 equals 0. So this one is also not going to cross the x-axis and therefore not have any real roots. Let me show you what happens as I go to solve this. If I subtract 49 from each side, I have x squared equals negative 49. If you go and on your calculator try to find the plus or minus root of square root of negative 49, it should give you something, some kind of an error message. It should say no real solutions, and that's exactly what it means. There are no real solutions to this. In other words, it has no roots. It does have solutions, but you'll have to come back for Algebra 2 to see what those solutions look like. But in terms of having x-intercepts or roots like we did up over here, this one does not have them. It matches this guy over here. It would actually be a parabola facing upward way up here at 49. So if this were 0, 49 up here, that's where my parabola would start and then take off from there. Okay. So gives you an idea of what's happening on those. Hopefully that's helpful.